Hello, students. So let's get into the second lecture on indices and exponential functions. So we streamed one video just an hour or two back where we understood the basic concepts of indices, and then we also trusted with the basic laws that govern the different algebra related to indices, right? And there I said you that there's a reason why we are also calling it as exponential functions, right? Exponential functions. So let's understand the rationale behind this nomenclature, and why do we call them as exponential functions. And then we would go ahead and solve a set of curated practice problems, so that we would be getting more hands-on on the laws related to indices that we studied in the previous lecture. Okay, so let's get going. So in mathematics, whenever we talk about a function, right? So one of the basic mathematical functions that we studied as a student was addition, right? So addition. So, and what does addition function do? So we know that addition functions takes two operands. This is the operator. So you have operator 1, you have operator 2, and when you add them using the addition operator, it yields one more result, right? So obviously that is the basic definition of function throughout mathematics, right? That you have a function, you supply some independent variable, and depending on the nature of the function, you get the outputs of that, right? So when we are saying that a to the power n equals to, it's nothing but a into a multiplied, a is multiplied with itself n times. So obviously following this rule, when we are saying 2 to the power 3, obviously that would be 8, right? So we know in mathematics, I can denote it, say, as a dependent variable y. Here, let me assume that I would change the indices. So let me say this is my independent variable x, and this was some base, right? So it may be a constant, it may be a variable, that's fine, right? So here I can say that here y equals to f of x. So if you see here, 8 equals to 2 to the power 3. So, and you can draw the analogy, right? So that is why we call it as an exponential function, right? So be it addition, be it subtraction, multiplication, your exponential calculations, or even logarithm, whatever. So you have so many mathematical functions. Now, one more practical aspect of understanding your exponential functions would be, say, we uh, we talk about nuclear reactors, right? Where one subatomic particle goes and it collides with one nucleus, and it breaks into, suppose, two, and assume that it produces two more neutrons. Then those two neutrons can go ahead and collide to each neutrons. So which means after the second wave, you have 2 into 2, four nucleus which have undergone that process. Similarly, if you think of the those all those four nucleus, right, which they have emitted two neutrons each, now you have eight. And then those eight would go ahead and they would explore two each more, right? So in that way, whenever we study about physics, or whenever we try to do a mathematical modeling of many things, exponential functions is a very common thing. So for example, as I said, be it your nuclear reactors, or today we talk about the growth of corona, right? So a coronavirus probably started infecting one person. That person, if he or she goes ahead and infect three more, probably they can infect three, each of them can infect probably three more. Obviously in real life, things would not be as simple as, they would always follow the same ratio, right, or the same exponent. But then, to put it very simply, either your growth of a bacteria, or even from a decay perspective. So we talk about the carbon dating and things of that nature. So be it growth, be it decay, many times your exponential functions become very important to study many things in physics, many things even in economics. So for example, we talk about the purchasing power of money, and we talk about the inflation rate. And there we say that if today 100 rupee is able to buy whatever things 100 rupee is able to buy, and if I say that, say, our inflation rate is 8%, so 1 plus 0.08 to the power n. So after 10 years, how much of, would be the purchasing power that will be defined by this, right? So exponential functions are used even for that. So there are many mathematical modeling situations which would be using the mathematical exponential functions, and we would look that in a greater detail when we go into our next lecture, and we'll solve a lot of problems related to mathematical modeling. But here we would concentrate on a set of curated practice problems which I shared in the thumbnail. So let's get going with that. And before that, let us pause for a minute, and then let us look into one law related to exponents, which I had not covered in our previous video. Okay, and that is this one. So say if I want to multiply minus 2 into minus 2 into minus 2 three times, right? So I want to multiply minus 2 three times with itself. So following the basic, your rule of exponents, right? So that is rule number one. I can directly write it as minus 2 to the power 3, right? Now, I can write it as minus 2 to the power 3. Now, whenever say I'm saying that a number 51, can I rewrite number 51 as 1 into 51? So we know that's a obviously, that is obviously, acceptable, right? So rather than minus 2, can I write it like this, that minus 1 into 2 to the power 3? Okay, and then in our exponents we had a rule that ab to the power m equals to a to the power m into b to the power m, right? So using this rule I can rewrite this as minus 1 to the power 3 into 2 to the power 3, right? Now, if you see, things have been much simpler. 2 to the power 3, very easy to calculate. I'll say this is 8, and minus 1 to the power 3. Just see that if I multiply minus 1 with minus 1, I'll get 1. If I multiply minus 1 three times with itself, I'll get minus 1. If I multiply 4 times, right, I'll again get 1. So what we are trying to explain here is minus 1 to the power n would always be 1 if n is even, and minus 1 to the power n will be minus 1 if n is odd, right? And here minus 1 to the power 3 is 3 is obviously odd, so this will be minus 1 into 8, so that is minus 8. So the law that we want to understand from this example is, or the generalization that we want to do from here is, minus a to the power n will be a positive if your n is even, right? And it would be negative if n is odd. And the reason is very simple. Any minus number would obviously can be written as minus 1 into the positive conjugate of that, and that much to the power something. Following the same steps, it would either have minus 1 to the power n, and n can be odd or even, and based on that the sign would be determined, and the other part would always be positive. So that's why when this part is positive, uh, and that is possible only when n is even. That time you get a positive number, and when it is not, you get a negative number. So this is one last law that we would have. With that, we come to the end of the laws related to indices. And now let us go ahead and let us practice this curated practice problems so that we will get a better understanding of all the laws related to exponential functions or indices that we have studied so far in our first video and things in this video also, right? So let's start with the first one, that minus half minus half to the, or say okay, uh, let's go with this, minus half to the power minus 5. Okay, minus half to the power minus 5. So the first thing is, we know a to the power minus n equals to 1 by a to the power n. We have studied this as one of the laws in our previous video. Or because raising something to a negative power is not by default defined, obviously we use this law. And using this law, I can write this is nothing but I can write this one as 1 by minus half to the power 5, right? Very simple. Now, 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 negative number raised to power 5, right? So obviously the answer would be negative. And if you see here, 1 by this portion can be written as 1 to the power 5 by 2 to the power 5, and we have a negative here, so that is minus 1 to the power 5, right? So okay, we can write it like this. Now if you see, your equal to sign is against this one, so obviously this would go to your numerator, and it would yield 2 to the power 5 by minus 1 divided by 1. So minus 1 into 1, minus 1 into 1, obviously I can write it as minus 1. So obviously the answer would be 2 to the power 5 is 32. Anything by minus 1 is obviously minus of that number. So minus 32 would be the answer. Here intentionally I have followed all the small intermediate steps also, and once you are a little used to with this, you can obviously jump those steps. But initially, for understanding, let us understand them step by step. And one more thing, I would encourage you to write down the reason of any step. So here we should write that because a by b to the power n equals to a to the power n by b to the power n, right? So that we will get more used to with all the laws of indices. Now, let's go to the next simple practice problem, okay? That is minus 3 to the power 4, okay? Minus 3 to the power 4. First and foremost thing, so obviously I have got a negative number and the index is an even number. So obviously my answer should be a positive number only. Now, minus 3 can be rewritten as minus 1 into 3 to the power 4, right? And now I can rewrite it as minus 1 to the power 4 into 3 to the power 4. And let's write the reason that ab to the power m is nothing but a to the power m into b to the power m. Again, students, I would recommend to write the reason, because many times I have seen in software industry that when people do coding, they find it a very tough task to write the comments. And that is probably because of the fact that as a students, people don't have the habit of writing the reason. And they feel as a bottleneck when they grow up and they become a programmer or a coder, right? So I would strongly recommend to write the reasoning as well. So from here, obviously the next thing is minus 1 to an even power is obviously plus 1. We have already studied this in one of our laws, into 3 to the power 4. That is nothing but 81. So answer is 81. Negative number raised to an even index yielding a positive answer, right? So we are again back to other law which we studied at the starting of this session. Okay, so quickly note it down and then we'll go to the next practice problem. Okay, so let's go to the next practice problem. And the next practice problem is I have slightly changed the index, and the next number is minus 3 to the power minus 4, right? Minus 3 to the power minus 4. So first thing, let us apply a to the power minus n equals to 1 by a to the power n, because my index is raised to a negative integer, right? So I'll rewrite it as 1 by minus 3 to the power 4, and obviously this is the reason why I am doing that. Okay, now again the same set of steps. 1 by minus 3 can be written as minus 1 into 3 whole to the power 4, right? And this can be written as 1 by minus 1 to the power 4 into 3 to the power 4. And again, because AB raised to the power m is nothing but A raised to the power m multiplied with B raised to the power m, right? So which would yield? Now, minus 1 raised to an even power would obviously be plus 1 into 3 to the power 4 is nothing but 81. I have 1 in the numerator, so my answer becomes 1 by 81, right? 1 by 81, and this is my answer here. Okay, okay, fair enough. So just note it down, and then we will go to our next practice problem on this. Okay, perfect. So let's keep moving. So in the next practice problem, we would understand one more property of indices. Yes, we have already studied it in the laws that we have studied so far, but we will see the use of it here. So say 25 to the power 3 by 4. What does it mean? Right? So we know that I can rewrite it as 25 to the power 3 whole to the power 1 by 4, and the reason is we know a to the power m to the power n is nothing but a to the power mn. So see, something is raised to a power 3 by 4. So it is not a direct integer. So I cannot multiply 25 with itself 3 by 4 times and find an answer. So I use the property because I know that there's a numerator, there's a denominator. So I have just separated them. So 3 by 4, I have put it as 3 into 1 by 4. Now, when my power is a product of two things, I can express it as product of the first factor whole to the product of the second factor. So that's why I put it as 25 to the power 3 to the power 1 by 4. Or if someone wants, he or she may write this also, 25 to the power 1 by 4 whole to the power 3. This is also right. Both are right. Okay, because obviously 3 by 4 can be written as 3 into 1 by 4 or 1 by 4 into 3. Both are equally correct. So let me follow this one. Okay, so if I say 25 to the power 3, now what do we mean by power 1 by n? So we know a to the power 1 by n is nothing but nth root of a. So this we have studied as one of the property in our first lecture. So I can write it 25 to the power 3 and then the fourth root of that, right? So now I can find out uh, using calculator. So I am not having a calculator now, so you can just find it out that one, that whatever is the value of 25 to the power 3 and take the fourth root of that, whatever you get, that is the answer. But process wise, these are the steps that we are supposed to follow for this problem. Okay, so sometimes when we have a fraction in the power, students get confused. So I will recommend you to note it down, and then we'll go to our next practice problem. Okay, So friends, so let's go to our next practice problem. I hope you would have already noted it down. Okay, so our next practice problem is something related to our exponential equations. So far, so in the first four problems, we just tried to solve the value, and now we want to solve it for getting the value of x. So my problem is 25 to the power x plus 1 equals to 5. Okay, now here let us understand the aim with which we should operate on any of these kind of problems. Okay, so we know that if a to the power b equals to a to the power c, then I can say b equals to c for all a that is not equal to 0 and 1. So let's assume that that's taken here. So this is the property which we want to use. Okay, and that obviously means my base on both the sides should be equal. So first and foremost thing, let me express both the sides as exponential functions, right? So left side is already an exponential function, 25 to the power x plus 1, whereas my right side is not an exponential function. So I can write it as 5 to the power 1, and we can write because a to the power 1 equals to a. So that's why I'm again insisting that let's keep writing the rational. That would help a lot in the longer run. Okay. Now if we see, now can I write x plus 1 equals to 1, right? Absolutely wrong. Why? Because base on my right hand side is 5 and base of my left hand side is 25. So I have two choices. Either I need to ensure that my base on right hand side also becomes 25, right? Or my base on the left hand side should become 5. If I can do, then only I can apply the next method, right? Or the laws that we have studied. So let me take the simpler route. So 25 can be expressed as 5 to the power 2, and rest I have x plus 1, so I'll retain x plus 1, that is equals to 5 to the power 1, right? Now here I can apply another law which we had studied, that a to the power m whole to the power n is nothing but a to the power mn. So using that, I can write it as 5 to the power 2 whole to the power x plus 1. That is nothing but 5 into 5 to the power 2 into x plus 1, right? That is equals to 5 to the power 1. And write down the reason that a to the power m whole to the power n is nothing but a to the power mn. Now my base on both sides are equal, and that's why I can write 2 to the power 2 into x plus 1 equals to 5. And now it's a very simple algebraic solution, right? Linear algebraic solution. So I get 2x, I'll multiply 2 with obviously this one, so expanding it, it becomes 2x plus 2 equals to 5, or 2x, I'll take this 2 to this side, so it will be 5 minus 2, or 2x equals to 3, or x equals to 3 by 2. Answer. So this is one way of finding it out. Now, I said you that in this step, we can do a bifurcation. So now let me show you that what would be the other way of solving it. Okay. So till this step, everything is same. I said you that I can either make the base of left hand side as 5 or base of right hand side as 25. Now, I write all. So 25 to the power x plus 1, and right hand side can be written as, I can write it, this one is nothing but root over of 25 to the power 1, right? And root over of 25 is nothing but 25 to the power x plus 1. Root over of 25 is nothing but 25 to the power half, and you can write the reason, whole to the power 1. Anything to the power 1 is that thing only, so I'll written it as 25 to the power half. Now if you see, here my base is 25, here the base is 25. So now I can write x plus 1 equal to 1 by 2, right? So obviously obviously your x equal to half minus 1. So it looks like there is some calculation error somewhere. Okay. Okay, but anyways, so this is the method in which we need to solve it. Okay, so let us go to our next practice problem. Okay, that is 9 to the power x. 9 to the power x equals to 27 to the power 2 minus 2x. 9 to the power x equals to 27 to the power 2 minus 2x. So first and foremost thing, this is very simple, that I need to ensure that either my right side I should express as a base of 9, and left hand side I should express as a base of 27. If I can do either of these, I can apply my law. But to make things even simpler, can I express my left hand side as a base of 3? So I can say it as 3 to the power 2 whole to the power x, and right hand side can be written as 3 to the power 3. So 27 I have written as 3 to the power 3, and then the rest is unchanged. So 2 minus 2x, right? So obviously 3 to the power 2 to the power x is nothing but 3 to the power 2x. Again, the same law, that a to the power m to the power n is nothing but a to the power mn. So I multiply 2 and x. Similarly, here I can write 3 to the power 3 multiplied with this 3 into 2 minus 2x, right? So which is nothing but, now base of both this LHS and RHS are same. So that's why obviously I can write 2x is nothing but 3 into 2, 6 minus 3 into minus 2x, that is nothing but minus 6x. So 6 minus 6x. Or obviously, if I bring this 6x to this side of the equation, this will be 2x plus 6x equals to 6, or 8x equals to 6. Obviously, x equals to 6 by 8, that is nothing but your 3 by 4, and that's the answer, right? So yeah, so this is the next practice problem. Okay, now I once you are done with this, then we can move to the next practice problem, and that is again we will understand few more properties obviously over there. Okay, so let's go into the next one. So the next practice problem is 2 to the power x into 1 by 32 equals to 64, right? And here also we would apply the same technique. So I need to express every term in this equation as an exponent to the common base. And if you notice it carefully, you will be able to appreciate that this can be expressed as an exponent of 2. This can be expressed as an exponent of 2. And this is anyways already expressed as an exponent of 2. So I can rewrite it as 2 to the power x into 1 by 32. 1 by 32 can be written as 1 by 32 is nothing but 2 to the power 5 equals to 64. 64 is nothing but 2 to the power 6. Now, here I'll apply my property of indices. And we know that a to the power 1 by a to the power n is nothing but a to the power minus n, right? So 1 by 2 to the power 5 can be written as 2 to the power minus 5. So a 1 by a to the power n is nothing but a to the power minus n into 2 to the power x. So we are not changing it. That is equals to 2 to the power 6. Now, obviously, a simple law of indices, when you have a to the power m into a to the power n, that is nothing but a to the power m plus n. So x plus minus 5, that is nothing but x plus minus 5 equals to 2 to the power 6. Or I can say x plus minus 5 is nothing but x minus 5 equals to 6. I have removed the base also. So obviously my x will be 6 plus 5, 6 plus 5, that is 11, and that's the answer, right? So yeah, you may just note it down, and then we will go to the last practice problem. So here the interesting thing is we have given it as a fraction. I mean 1 by 2 to the power, so that your power would be negative. So that is the obviously that is the property where I wanted to draw your attention to. Okay. Now let's go to the last practice problem of this series. Okay, and that is 243 to the power k plus 2 into 9 to the power 3k minus 1 equals to 27, right? So now again, my aim is same. I want to express each term in the equation as exponent of the same thing, right? So here, this can be expressed in exponent of 3, this can be expressed in exponent of 3, and this also can be expressed in exponent of 3. How? 2 plus 4 is 6, 6 plus 3 is 9, and then I know that 3 to the power, I can express it as 3 to the power, right? So we know 3 to the power 3 is 27, 3 to the power 4 is 81, and 3 to the power 5 will be 81 into 3, that is nothing but 243. So I'll rewrite it as 3 to the power 5 whole to the power k plus 2 into 9 can be rewritten as 3 to the power 2 whole to the power 3k minus 1. See, I'm just changing the base. I'm not disturbing the indexes at all. Okay. Now, on the right hand side, 27 can be written as 3 to the power 3. Now, first part is done. I just need to apply some more property of indices, and I'll arrive at my solution. So, obviously, here 3 to the power 5 whole to the power k plus 2. So, obviously, I need to multiply 5 with k plus 2, and it becomes 3 into to the power 5 into k plus 2 into 3 to the power. Similarly, 2 into 3k minus 1, it will be 2 into 3k minus 1 equals to 3 to the power 3. Okay, and again, write down the reason that a to the power m to the power n is nothing but a to the power mn. We applied that property there. Okay, now the next one is here your base are same and two exponents are multiplied. So obviously, I need to add the indices to condense it to one base, right? So I can say 3 to the power 5k plus 10 plus 2 into 3k is 6k minus 2 into minus 1 is nothing but minus 2 equals to 3 to the power 3. Now, my base are non-zero, base are equal. So obviously my indices have to be equal. So this much must be equal to this much. Or I can write 5k plus 6k is nothing but 11k, 10 minus 2 is nothing but 8 equals to 3. Or 11k equals to, when this 8 comes to this side, this will be 3 plus 8, or 11k equals to 11, or k equals to 1, and that's your answer, right? So couple of things which we should notice in this entire curated practice problem set is whenever you are trying to solve your exponential equations, try to condense it to to the same base. If you can condense them all to the same base, obviously you can apply the different laws that we studied related to indices, and obviously that will help you solving the problem. So see you with more practice problems, especially on the word problems related to growth, decay, and all, and a lot of mathematical modeling in the next series of it. Thank you.